Hey everybody, I'm going to look like a giant today because down below is a little demo as I summarize the Spring Lab. I think these graphs, and I'm trying to think, is it super blurry? Is it focusing on this? See if I can go up and focus it. Well, it's going to be good enough for now. These should have been the initial results when you graphed our period versus mass, our period versus spring constant, and our period versus displacement. Now, I think most everyone got the comments as far as our period versus mass. When we didn't plot 0, 0, it tended to look linear. And so when we're gathering data, and what we need to do is kind of look at, well, what would happen if I have a really, really small mass? If I had 0 mass, clearly I'd have 0 period. That works for everything. If I have 0 spring constant, I've got 0 period. And if I've got 0 displacement, I'd have 0, right, period. But we got to think about really small, okay? So by really small mass, is that going to be the same or near anyone with 100 grams? And the answer is no. So we have to look at 0, 0 and evaluate that. And so we have to use a little bit of critical thinking, imagination based on our trends. And ultimately what we found out, our relationship, when we did the square root of the mass, gave us this nice linear trend. Now you had a k value was constant right there. As far as our spring constant, you found this inverse relationship, and then you found this, and it was really hard, it was really subtle. Again, if it were just not plotting that large, untested, super large k value, which then becomes really small when you take the inverse, right? If I have a really stiff spring, what's my period going to be? Practically 0, not necessarily like a 0.2 or 0.5 or whatever. So we kind of had this nested, right? So we were doing some linearization on steroids. It really was 1 over square root of k, and we had the mass was constant. Now, I didn't do displacement because ultimately our displacement ends up being a non-factor. And this one, we had something near horizontal. Again, these looked near horizontal, more of a slope, honestly, I think. But these looked near horizontal, and so let's plot 0, 0, first of all, and then think about it a little bit. And I know they're limited on what masses, but if we were pretty consistent in evaluating it, and we had like, some people had depending on their spring, 0.4, 0.45, like 0.46, 0.45, 0.44, 0.46. I mean, that is about as horizontal as you can get. Ways that you can evaluate, is that a big difference or not? Because if I zoom in, it could be a big difference. They could look really far apart. You can always use a percent difference to see. Or think about if I had a really, really small displacement, and this is why I've got this set up. If I have a really, really small displacement, right, do I have a non-existent period? And so I'm just going to go boop, like that. Now I'm going to compare that to something bigger. Right? And if my percent difference didn't convince me there's no impact of displacement, if we were doing this live in class, we could have done just a little bit of a tap and see that that period stays the same. So I've got no impact. Now, I get it. This becomes a challenging lab, okay? I wanted to make sure that when you guys finish this class, you kind of got part of a major issue of physics or a science and scientific methods and approaches. Being able to look at data and evaluate data can get us a relationship. Now, it can get us more than a relationship, but right now, I know that I've got some sort of constant and a relationship like this. So these are proportional. If I increase the mass, I'm going to increase my period, but only by a square root relationship. If I increase my spring constant, I'm going to decrease my period, and that should make sense also. I'm hoping we get this conceptual, intuitive approach. Increase the spring constant, decrease the period. Okay? What I could have done, if I had some data, right, you would have gotten t equals some slope, and I'm just going to use a c for a constant, times the square root of mass. Okay? And then down here, and this constant would have been a specific number, right? And on this one, I would have had t is equal to some constant, maybe I do 1 and 2, times 1 over the square root of k. What we would find if we plugged in the k value, or if we plugged in the constant mass into here, or if we plugged in the constant k in there, we would have found, instead of a proportional statement, we would have found our number to be close to 6.28, which is pretty stinking cool, okay? So I wanted to kind of demo something. As a result, what did we find, okay? We found this equation, okay? We found this equation, and we can utilize this equation in any setup, okay? So what I did is I used this equation to find out what my period would be for this setup. So I had to find the k value. I ended up finding a k value, 2 pi, and I found the k value is 3.07. And then my mass on there is 50 gram, which is 0.05 kilograms. And what I found out is my period was 0.8, I think, what was it, 01, so really 0.8, and that's time, seconds per cycle, right? Now, I don't know if y'all remember, right? I don't know if y'all remember this. We did the Galloping Gertie that had what we call a natural frequency. Okay, do you guys remember that? Did I show you that? I hope I did. It involved adding energy to a system, okay? A frequency, right, is just 1 over t, and that is about 1.25 for this scenario, okay? Now that is cycles per second, okay? So what I've got here, right, is a metronome, okay? And right now it's at 46, okay? And that's beats per minute, okay? What do I get as far as my frequency for this spring? I'd have to multiply by 60, and when I multiply by 60 cycles per minute, or beats per minute, that is 74.8 beats, or cycles, per minute, okay? So what I'm going to do is I'm going to change this to about, well, I don't have decimals, so I'll change to 75 beats per minute. And you can kind of see that flashing light. Bah. Okay. And I'm going to try to let it go at that beat. Ba, 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 ba. Almost right on it, right? Which is kind of cool, because I just did some measuring of centimeters and displacement to get the k value. I've got the mass, and I've essentially found that frequency, okay? Now here's the cooler part, okay? This is what we call our natural frequency. For this spring and this mass, this item, this setup, this, I'm not going to change the spring anymore, I'm not going to change the mass. This has a natural frequency. And if I apply a beat, or a force, at this pace, or any variation of this pace, like any whole number variation of it. So instead of 775, if I did it at every 150, I would have this situation where I'm adding energy to it. Da, 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 da. Oh, I can't get it. Do you see how I keep adding energy, and that should kind of coincide, little small hits, and it's adding energy to the spring. Now I'm going to change to 70. Da, 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 da. If I'm just a little off, right, it's hard to do. Ba, 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 ba. It gets kind of jumbled, right? And it doesn't go into that natural frequency. It starts canceling each other out, okay? So this, to me, is kind of cool. We call that F of O. So if I were to hit with 4 times the F of O, which, I don't know, that's 150, about 300, right, cycles per minute. Oh, that'd be very fast. But I could lengthen it to 3. Whoops. 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1. Ah! Ah! Do you guys kind of get that point? I can find my frequency of this setup based on finding the period, and it's got an oscillatory motion, right, of that frequency. If I can add energy to that system if I just tap, right? If I add a beat, I add a small force at that natural frequency. I keep adding and adding and adding energy to the system, which I think is pretty cool. So this is a Spring Lab summary. This equation right here, you'll find on the AP test equation sheet. We'll be expected to know what information to find it, how to use that, and you guys are doing a discussion board on pendulums right now, hopefully looking at graphs, not necessarily posting graphs, but drawing conclusions from your graphs. I'm going to do the same thing today and post my results probably tomorrow to be able to discuss it. And then I think I'm going to give you guys a little action plan to see if you can recreate the scenario, okay? I hope you're well, and I hope that explains or helps you visualize this equation. And please know, I know the lab was long and pretty intense, and you got some comments based on those, but the intent was just kind of a capstone, in a way, of this class, making sure that you're able to explore physical phenomena, look at data, and draw conclusions. All right? See you later. Bye.